So for the second learning module of this chapter, I just wanted to get you set up on the first problem on the second portion of the final exam. Way too many first and seconds there. That involves the integral-based computation of moment of inertia. So what you're going to be asked to do is to determine the moment of inertia of a power function where the power is arbitrary to the nth power about the y-axis in this case. So this is a really easy one because all that you have to do is take and create these little vertical rectangular infinitesimal areas. Remember that each of them will have a moment of inertia about the y-axis as the square of the perpendicular distance from the y-axis to the rectangle. Remember, that's just x for any value of x, which would mean any of these rectangles under the curve. So that will be your distance squared, x squared, times the area of this rectangle, which will just generally be the width, which is dx, times the height, which you can express as a function of x using this formula. So in general, for the little rectangle, its infinitesimal moment of inertia will be x squared dA. You can write dA as y dx. You can write y as b over a to the n, x to the n. Just do a little bit of algebra here and combine the terms x squared and x to the n by adding the exponents. So this will be x to the n plus 2. Don't forget your constant, b over a to the n. And just basically, in order to determine the total moment of inertia, add up through integration the infinitesimal moment of inertia of each of these rectangles. So we're going to integrate all of them, and we're going to do that by allowing x to vary from 0 to a. And this is just going to be a power function. This constant will be able to come out of the integral. Just add 1 to the power here and divide by the new power, and just be careful with your algebra. And you should be able to compute this as a algebraic function of the parameters of the geometry, a and b. So hopefully that is helpful to you, and hopefully this is an easy problem. So good luck.